Welcome back to Statistical Data Analysis 2. In the lecture of today, we're going to have a look at several important issues that often arise when we are working in practice in the real world with linear models and how to address them. Consider for a moment the equation here on the right side. That is the equation of linear regression, and to be very precise, the equation of multiple linear regression. Multiple linear regression means that we have more than one predictor variable. We could have three, for example. So here, this would describe a model with this first predictor variable, xi1, like predictor or independent variable, that's synonym. Then we have xi2, the second one, xi3, the third one, and we could even add more of them, right? So this is, in this case, it's three main effects of each main effect of like a different predictor variable. And this equation describes the linear relationship in the population, meaning that we have the true beta values here. So beta 0, beta 1, beta 2, beta 3, basically the unknown parameters, but which at least we can assume to have some true value in the real world. And so this is in a way the linear regression equation in the population. In a specific sample that we have at hand, maybe by running an experiment, we would have only estimates for beta, okay? So instead of having the true beta values, we would have these hat beta values, which we can also sometimes see written as just B, like the Latin B, which is also just a way to write like the estimate, the sample estimate for the beta parameter, be it beta 0, the intercept, beta 1, the first slope, beta 2, the second slope, and so on. Now, in general, we can ask ourselves, why should we use multiple linear regression, or like when does it make sense to do that? And that applies not only to these simple linear regression models, but by extension also to linear mixed effects models that we might want to fit on repeated measures data. So the thing we have to consider is that the dependent variable of interest is often complex and cannot be explained by a single variable. So it might be the case that, let's say we have our classical example of psychological symptoms, which is our dependent variable, and then we have the stress level, which is one predictor, and then maybe the gender, which is another predictor. And it could be that both of them have some reasonable relation, like effect on the dependent variables. So it would be good to be able to find the effect of each of them in a single model. So that's one reason why we want to maybe put both predictors in there, or potentially even 3 or 4 predictors, if we have a reasonable cause to believe that each of the predictors we include could in principle affect the values of the dependent variable. And so you could also ask yourself, okay, but couldn't we also solve this by fitting one model for each predictor? Like, let's say to fit one model that tries to predict stress level only based on, that tries to predict psychological symptoms only based on stress level, and a separate model that tries to predict psychological symptoms only based on gender. Like, why wouldn't that already solve our problem? Okay, I mean, one issue is that maybe we even want to include the interaction term between the two predictors in the model. In that case, obviously, we need to fit one model including both predictors and their interaction. But even if we just look at additive main effects, like we don't include the interaction, there is still a reason why it makes a difference to fit one multiple linear regression with both predictors as opposed to two separate simple linear regressions with only one predictor each. The reason why that is what we're going to look at now. So let's stay for a moment with our example. So we could have two hypotheses, right? So one about the first predictor, that the symptoms can be predicted by stress. The second one, that the symptoms can be predicted by gender. And now the question is how to do this. Will we run one model with both main effects included, or will we run two separate models? Spoiler alert, we should run one model, and we're going to see now what the problem would be if we would just run two separate models. So the reason why we always prefer to run a multiple linear regression with all our predictors of interest in the same model is the possible correlation between predictors. So in our example, if it was the case that stress and gender were completely independent, then okay, if that was the case, then one model with two predictors or two models with only one predictor each would give us exactly the same results. The problem arises though in case stress and gender are not perfectly independent of each other. So let's say, I mean, this is not necessarily true, but let's say for the sake of the argument that it was the case that women tend to experience more stress than men, like on average. In that case, we would have one predictor gender, men versus women, and the other predictor stress, and there would be a correlation between them. And in that case, the results of fitting one multiple linear regression to predict psychological symptoms would be different from fitting two separate models. The reason lies precisely in the fact that our predictors would be moderately correlated, let's say. And in fact, psychological and linguistic variables often display moderate or even strong correlations with one another. So some very prominent examples could be, on the one hand, by item predictors, like if you have different stimuli, different words or different sentences in your psycholinguistic experiment, then you might have some word property like lexical frequency, like how often the word appears in sentences in the particular language in general. For example, you might have the article the or the article an in English, which is probably quite frequent, okay? And you might have the idea maybe that frequent words are read faster than not so frequent words. For example, the word independent is, I guess, less frequent than the word the or a, right? But the problem is if you just fit a simple linear regression, let's say, trying to predict the reading time of the word by its frequency, you would get one slope, okay, for frequency, but the problem is that you don't really know to what extent the variance in the reading time is really explained by frequency alone, or maybe just by, word length. Because in the end, there's a strong correlation. It's not a perfect correlation, of course, but there's a strong correlation between a word being shorter is often associated with it being more frequent, like the and a, and a word being longer, like independent, with being not so frequent, like quite a rare word. So you really wouldn't know so much about how lexical frequency influences reading times if you just put one slope for frequency and then completely ignore the variance that's already sort of trivially explained by word length, okay? Because they share a lot of variance. It's not exactly that they mean the same thing, obviously they don't, but the fact that they have so much shared variance means that we would miss something if we just fit one model with a single predictor, right? And for by participant predictors, we could have things like, okay, if we have, for example, the age of a person in years and their years of education, then this is also obviously correlated. So not perfectly again, but we can expect that maybe an older person will also have more years of education than a younger person. So these variables are not interchangeable, but they have a strong correlation between them. These are like very, very like practice-like examples of predictors that could be correlated and where this problem would arise. Also things like language profiles, proficiency, and age of acquisition. If you've acquired a language early in life, then you're probably more likely to be proficient or use it often, right? So all these predictors overlap to some extent, like they have some shared variance. And now, for our modeling question, the thing that we should ask ourselves is like, what are the potential consequences of such correlations? Because as I just said, there is some shared explanatory variance of reading times, let's say, of both frequency and word length. And if or like for the language example, let's say I find an effect of proficiency in a simple linear regression, so I have some score of how proficient people are in a language. Now, how can I really be sure that this is not driven by the correlation between age and proficiency? Because maybe more proficient participants are older, okay? So all these kinds of questions arise and problems arise when we don't really consider the possible correlation between different predictors of interest. So what can we do about this? I mean, one option for sure could be to balance everything across our multiple predictors. That is, for example, making sure when we have words and we are interested in their frequency, that we have just as many short as long words that have the same frequency for each sort of level of frequency we might consider, so that there is no correlation between length and frequency in our particular sample that we want to test. Or let's say we test different people who speak languages, and we want to make sure that the group of proficient participants and the group of less proficient participants that we include in our study are sampled in such a way that they do not differ in age, if there was this correlation between age and proficiency. The problem of this approach is that it can be impractical to equate conditions or groups in all of the variables that could potentially act as confounds. That is, like, confounds is the word that describes this potential other predictor that we don't account, which might be correlated with our predictor of interest. So all of these possible confounds, like, we can't really sample. Oftentimes we can't really sample in such a way that there is really no such confounding, no such correlation in our sample. And also, like, if we have like an imbalanced sample where people of different, like, and also if we have a sample where the correlation is still there, like, let's say two different proficiency groups, and indeed we have the situation that the more proficient ones are also older and the less proficient ones are also a bit younger. I mean, we could also, when we tested them and then see, okay, but there is this problem of correlation between age and proficiency, let's maybe remove some data points in such a way that we end up with a subset of data points where the correlation is not there anymore. Like, let's say we have removed some of the older people from our proficient sample, or some of the younger people from our less proficient sample, in order to restore, like, the situation that there is no correlation in our sample anymore between proficiency and age. But the problem is, if our original sample was, like, balanced, like we had an equal number of proficient and non-proficient people, then if we remove data points here and there, we are very likely to break the balance again and to end up with a sample that overall is not balanced anymore. So that's also not a great solution. And also we lose some information, right? Because as soon as we start excluding data points, we also, limit ourselves in an artificial way as to which information we include. Like, why should we include the information of a few of the older people that are proficient just in order to restore this uncorrelatedness of our predictors by force? So that's not a great solution. Option 2 is a great solution. Option 2 is to include different variables, let's say age and proficiency, within the same model in a multiple linear regression model. And this solves the issue, and we're going to see why, but that's precisely like the usefulness of a multiple regression model. So the reason why it's useful is that basically by including both predictors, age and proficiency, let's say, we're automatically disentangling the effects of these predictors. And really the slope that we will have for proficiency will be just the variance of proficiency, of which already we have taken away the confound with age. And likewise, the slope we find for age will be just the pure age variance, of which we have taken away the confound by proficiency. But still, the overall fitted model will also include the explanatory power that they have together, like the sort of shared variance in the overall explained variance. Like, the residuals will still not include, let's say, the part of age and proficiency which is conjointly predictive of whatever the dependent variable is. So I guess that sounds a bit abstract, so visualization could help maybe. So let's imagine our other example again with frequency and length. So we want to find out how word frequency predicts reading times, RTs, okay? And we have this worry, let's say, about the potential confound with word length, which also trivially predicts reading times and is correlated to some extent with frequency, with shorter words being more frequent and longer words being less frequent. Now what you see here in this Venn diagram is sort of a visualization of the different portions of variance that each of the three variables here have. So our dependent variable RT, like this entire circle, is just the variance of RT, the variation across our population and, in that case, our experimental sample. And this full circle of frequency is like all the variation in frequency, and this full circle of length is like all the variation of length. Now, this intersection of length and frequency is like their correlation, okay? That's maybe this property, this issue that, there is, to some extent, we can explain frequency by length and vice versa, because there is some tendency, not a perfect tendency, but some tendency in this area C and D, that more frequent words, as I just said, are also often shorter. So that's like the intersection in this Venn diagram of length and frequency, and that's like their correlation. And the problem is if we just did a simple linear regression predicting RTs from frequency alone, in that case we would basically, like, the model would try to find this shared variance between frequency and RT, which is this area A and C together. But it wouldn't take into account that this area C is also correlated with length. So it would just give you this naive output of saying like the entire effect of frequency is like this whole thing, right? Whereas in reality, I mean, we can be sure about A because it's a pure frequency effect, but like C is sort of this thing where frequency or length could be used as an explanation. Like, it's not really clear which one is causing it. And likewise the other way around. Like, if we would just want to look at the effect of length, then we're not taking into account that this portion of shared variance with RT is actually also shared with frequency. So basically, if you fit two separate simple linear regression models, you would get this A and C together as the variance that the model thinks frequency explains in the first model, just including frequency, and the second model, only including length, would assume that this variance C and B together is what length explains in RT. So each time it would, fail to account for this relation between frequency and length. And now the multiple regression will do the following. It will, if you include like both frequency and length in one model, then the slope you get for frequency is really just about this area A, okay? And it already takes into account that C is not really necessarily what we're after, because it's also actually something that's related to length. And likewise, the slope that we find for length will then really just be this area B here, but not this part C, which is again also explained by frequency. Overall, the fitted model will still also respect this variance C, like it will not disregard it. It will still sort of, the overall residuals left will still also not include the C anymore. Like, all of this A, C, B will be explained in a multiple linear regression model overall. Like, there are less residuals than in any of the two separate models. But the slopes we get as an estimate out of the model, the estimated beta 1 for frequency and the estimated beta 2 for length, those will really just be about the pure variance of each predictor. Like, it will already somehow account for and factor out, let's say, this shared variance that it also has with the other predictor. And this way, we can very nicely, control each predictor's effect for potential correlation of the other and sort of filter this correlation out and really end up with estimates of our effect that's in a way really purely about frequency or really purely about length when we look at the model output. And this allows us, well, to ask questions like, how much does predictor x1 explain variance in the outcome variable beyond what is already explained by predictor x2? And a way to do this would be to run model comparisons. So we could first fit model 1, let's say, which just includes the main effect of frequency on the outcome variable, in this case reading time. And in this diagram from before, in this Venn diagram, the estimate for frequency would basically be all about this entire variance A plus C. So everything that's sort of the shared variance between our predictor variable frequency and the outcome variable reading time. So A and C would be what would be explained by model 1. And we could fit model 2, which will be including both the main effect of frequency and the main effect of length. So this model 2 will now explain A, C, and B, like all of this variance in the outcome variable. And so the residuals would now be E, it would be like less variance that remains unexplained. So A, C, and B, these portions of the variance in reading times, is now explained by model 2. So recall that model 2 explains A, C, and B, whereas model 1 only explained A and C. And now I could do something like asking, okay, what is the unique contribution of word length to reading times that is not including the shared part that's also covarying with frequency? So B in this case, like I could ask the question now, what is B? What is this unique contribution of the factor length, of the predictor length? And I could achieve this conceptually sort of by doing model 2 minus model 1. So like by taking the amount of variance explained by model 2, which is all of this, A, C, and B, and subtracting from it the amount of variance that is explained by model 1, that is A and C. So what remains, if doing A plus C plus B minus A plus C, together in brackets, I will have B, right? That will give me the unique variance that is common between the reading times and the length, but is not related to frequency 2. And one way to do this, like an excellent way that we are already familiar with to do such model comparisons, would be to run this likelihood ratio test using the ANOVA function that we are already familiar with. This whole topic brings us to the concept of multicollinearity, which is precisely referring to these kinds of situations. So whenever we have multiple predictors and there is a like reasonable degree of correlation between them, then what we are facing is the issue of multicollinearity. And as long as multicollinearity is not too high among our 2 or possibly 3 or 4 or whatever the number of predictors we have, as long as it's like not too big, the correlation, it's still okay. Like we can, actually even exploit the fact that we can put multiple predictors into one model and thereby find slopes for only the unique contribution of each. The problem is really if the correlation between predictors is not just like moderate, but is very high. In that case, it can happen that estimates and slopes, and by extension also p-values, change rather dramatically if the correlation between predictors becomes more extreme. And it can even happen that the model shows no effect of any predictor, even though if we had taken our predictors separately, each of them would have shown a significant effect on the dependent variable. So some correlation is fine and we can deal with it, by putting things into the same model. But if it gets too out of hand and like the variables, the 2 predictors are almost the same thing, in that case it can be problematic. So here you can see another Venn diagram. So imagine we had 2 predictors, x1 and x2, could be frequency and length, but imagine something that's almost the same thing, right? Where like x1 and x2 are hugely correlated among each other. If we now try to put them both into the same multiple linear regression to describe their effect on our outcome variable A in this case, here like the slope for x1 would just be like this tiny portion of variance, and the slope for x2 would be just this tiny portion of variance. And oftentimes this also has like mathematical problematic consequences, meaning that under the hood, this matrix algebra that tries to find the best fitting values can not really work anymore, because this matrix, which is like the design matrix transposed times the design matrix again, which we, as we saw like 2 weeks ago, we need in order to estimate our beta parameter values using these matrix operations. That matrix can be nearly singular, and this will then result in an error because R can't properly find the solution anymore because the math breaks down basically. So that's a possible dramatic consequence of high degrees of multicollinearity. There is a way to check for multicollinearity, and it is called the variance inflation factor. The variance inflation factor is basically a metric that we can compute once we have fitted a multiple linear regression model, and it tells us basically how big the multicollinearity is. Now, we can compute this variance inflation factor for a particular predictor in that model. Let's say in our example of frequency and length, we could compute it for frequency, and then we could compute it for length. But it also works for models with more than just 2 predictors, let's say 4 or 5 or 6 of them, or as many as you like. And this is the equation that gives you the variance inflation factor for a predictor j, let's say. And so it's basically 1 divided by 1 minus r squared j. This r squared j is called the coefficient of determination for that predictor j. You can think of it basically as describing the amount of variance in j that's already explained by all the other predictors. So in this case, for example, the the r squared for frequency would be all the variance in frequency that's already explained by length, in this case c and d. But if we had like another predictor, then it would also include the shared variance of frequency with the other predictor. So it basically tells us how much variance in predictor j can already be explained by all the other predictors that are in my model. And so that's the rj. And like if this r squared j, not rj, if that r squared j is very high, then we can assume that probably including this predictor is not really important for explaining additional variance in the outcome variable, because most of it will already kind of be explained by its correlation with other predictors. So this is the r squared j, and this r squared j is literally a ratio. So if it is 0, it means that 0% of the variance of our predictor j is explained by other predictors, by all the others we've included, combined. Whereas if this r squared would be 1, that would mean that the entire variance of my predictor frequency, let's say, my predictor j, would be already explained by other predictors. That means that there's no unique variance left that's just based on frequency alone. So it can range between 0 and 1, that are its boundaries for this r squared. Like it tells us how much variance is explained of the predictor. And the VIF, the variance inflation factor, as you can see, has this term. It is 1 divided by 1 minus r squared. As a consequence, it will be exactly 1. That's the lowest possible value it can have when there is no correlation, like no multicollinearity at all. So imagine that r squared was 0 and plug this into this term. In that case, you have 1 divided by 1 minus 0, so you have 1. That's the lowest possible, the best possible VIF you can have, which means that the predictor is completely unique. There is no variance that it shares with other predictors. Whereas as you increase r squared towards its maximum possible value of 1, the VIF will go towards infinity. So it will become a very large numbers. And I mean, if you would plug exactly 1 in here, you would even get an errors. But say you plug 0.99 into this, you would have 1 divided by 0.01. So that would be 100, let's say. So like a big VIF. So VIF is in principle ranges from 1, the lowest possible value, to possibly as high a number that you want. Okay. And so the VIF then also we can interpret it as a way of telling us how big the multicollinearity issue is. Now let's have a look at a concrete example in R and how we can compute the VIF once we have fitted a multiple linear regression model. So in this lexical decision, or for short LexDec dataset that we've worked with in the past, there are a bunch of variables associated with each observation of reading time. For example, the frequency of a word, but also the size of, I believe, the word family that it belongs to, okay? And so it might be that there is some correlation between those two. So if we fit a linear model predicting reading time based on these two main effects of frequency and family size, we can save it in a variable m, and then we can use the VIF function, VIF as in variance inflation factor, on that model, and it will give us the variance inflation factor for each of the included predictors. Here, as you can see, the variance inflation factor for frequency is 2, roughly 2.000 something. And it's the same actually for family size, which in a way is not surprising, because if you just have 2 predictors in the multiple linear regression, then it's equivalent to ask either, okay, what is the amount of variance in frequency already explained by length? It's this area C and D. Or conversely, asking what is the amount of variance in length, or in this case, family size, already explained by frequency. That's again C and D. So that's why R squared is identical, and also the variance inflation factor by extension will be identical here if we just have two predictors. Consider another example from the same data set. So there is also the property of words, which is the frequency that they appear in singular form or in plural form. And these are two separate columns in this data set. And obviously you can expect kind of those to actually encode almost the same thing, I guess, only in the opposite way. So it's not surprising that when we put them together into this multiple linear regression, we can see that, in fact, the variance inflation factor here, which is again the same for both, is rather high, like 4.68 something, right? So again, if the predictors were uncorrelated, the VIF would be near 1. That would be the optimal case. And there are different opinions on when a VIF becomes problematic. For example, Dobson and colleagues, like some statisticians, recommended that one should start to worry as soon as the variance inflation factor is greater than 5. So in that case, it would be rather problematic. So 2 or 4.6, maybe it's still okay-ish, but if you have a variance inflation factor greater than 5, then the predictors are like too correlated to just ignore this, okay? That's maybe the rule of thumb that one could apply. So maybe you ask yourself, okay, but if multicollinearity is such an issue to be like careful about, what can be done to avoid multicollinearity? So there are different strategies you could do. If you really see that, you have like a VIF of greater than 5 and that risks of like making your estimates not really interpretable because they're not really about a huge amount of variance in your predictors, but just about a tiny small amount that's still unique to each of them. If that's the case, then you could choose to, okay, maybe just keep one of the predictors and drop the other, right? So you could say, I don't know, if frequency and family size turned out to be like almost the same thing, sort of, you could say, okay, they are like so correlated with each other that it doesn't really make sense anymore to keep both of them in because they almost mean the same thing, and my slopes will then just represent this tiny portion of variance in each of them that's not really anymore substantial to what I'm after, basically. Then I could just think what's like the more important one and drop the other. Like the one that I'm more interested in conceptually is maybe the frequency, so I will drop the other in that case if I see that the multicollinearity is too high. If it's not too high, then it always would make sense to keep both, but if it's really too high, like VIF greater than 5, then indeed I have to like change gears and do something, and I could just pick one and drop the other. Another strategy could be to try to combine them in a way, so like maybe to construct a combined metric out of both of them, like sort of add the frequency and the family size together, or like multiply them with each other to like create a new kind of artificial predictor variable that sort of still encodes now the information about both of them in some new way. But obviously then you have to be careful, because then this is not anymore either frequency or family size, but something else entirely. So you would have to adjust your interpretation accordingly and like maybe give this new variable some name. So maybe you can call it some metric that you give your name or something, and then say that's my predictor. But you wouldn't really talk about just the effect of frequency or just the effect of family size anymore. So these are two things you could do if you see that indeed there is too much correlation between predictors to like still get sensible estimates. All right, the next topic that we want to talk about to some length is interactions. So as you may have heard or not, an interaction basically describes the effect of one predictor onto the effect magnitude of another predictor with regard to the dependent variable, to the outcome variable. Now that might sound a bit abstract, so we could make it concrete with a couple of examples. Let's say this one, where we have the same predictors that we talked about previously. So let's say we had reading times as a dv, dependent variable, and word frequency as one predictor and word length as the other. Now, if we would find that there is an effect of word frequency, okay, like that to some extent more frequent words are read faster and less frequent words are read slower, this might still not be the whole story, because it could be that this frequency effect itself is subject to change, like regarding to how big it is, depending on word length. So it could be that the frequency effect is stronger for longer words. That is, that if we just look at long words overall, just like rather long words, then among those rather long words, there is quite a big reading time gap depending on frequency. So like here for long words, frequency has a quite big impact on the reading time. Whereas for the group, let's say, of rather short words, of maybe just 3 or 4 letters, here frequency doesn't matter so much, like it doesn't have such a big impact on the reading time. If we had a situation like this, okay, then we would speak of there being an interaction, because now the effect magnitude of one predictor is subject to change depending on where we are on the other predictor. And you could think of many examples of this. Basically, anytime you have 2 or more predictors, you can speak about their potential interactions. And you can account for, like also model and estimate an interaction between parameters in R when you fit a linear model. And we're going to look at that now a bit more concretely. So here we have our stress symptoms 2 dataset again. Recall that is the one where we have psychological symptoms as the dependent variable, and we have 2 predictors, one being the stress level and the other being the gender, in this case just man or woman. And here we have like 2 scatter plots, one just for the men and one just for the women, each representing the relationship between stress level and psychological symptoms. So in a way you could like look at just one of them, just at the plot for men, and try to like draw the best fitting line that would be like as steep as your linear regression slope for stress. And you could do the same thing for the women. And then the interesting question would be like, if the slope for men is like this, let's say, is the slope for women the same? Or is it like a bit steeper or a bit less steep? Here intuitively it's maybe a bit steeper. So if the slope is not the same for men and women, but it's like changes, then we have an interaction, right? Because that means, in other words, that the gender has an impact on the effect magnitude of the stress level on the psychological symptoms. So we could first maybe just do a simple thing and try to run a regression test just for the effect of stress in women, sort of to see how large the slope is for women, like the best fitting line for women as opposed to the one for men. So we could say we create a subset of our data set after we've loaded it in using read, CSV, read table, and so on, of course. And we say we want the subset of this data set where the gender is woman. That is, we only have a data frame now that includes observations from women. So only these data on the right. This data is now discarded entirely. And we can fit a model, calling it m.women, for example, which will predict symptoms based on the stress level, simple linear regression, but only on this subset of data, which is about the women, okay? And if we look at the summary that this model gives us, like in R, we can see that, okay, we have some intercept, of course, and we have the slope for stress, meaning that there is a positive relation between the stress level scores and the psychological symptoms, because the slope is positive, and in fact it is even also significant. So there is a significant effect of stress level on psychological symptoms for women, and this effect size is 1.3365. So we could write down like effect size of stress on psychological symptoms, right, as a C, like psychology, okay. For women, we can see this effect size, meaning the effect size, you have to like also interpret the slope properly now. So it's basically in units of stress level, of psychological symptoms score units per stress level score unit. So like for each step on the scale of stress levels, you increase the value of the psychological symptoms by 1.33. Whatever these exact numbers mean, there are some scores from some psychological questionnaires, I guess, or something. So for women, we have beta 1, the slope estimate, het beta 1 is equal to 1.3365. And now we can look at the same thing but for men and see what we will have. So, okay, after plotting this best fitting line that represents, the slope here, the steepness is this 1.3365 exactly. The data are the same as in this plot on the right hand side, and only the stretching and squeezing of the plot is a bit different here, but it's all the same with the best fitting line. Now we could do the same, as I just said, for men. So we can create a new subset of the data, which is just about the data that pertains to men but not to women. And I could, save this again in a model, and I could run a model and save this into a variable called m.men in this case. And I can now print out the model summary again to see what I got here. So for the men, I could note down what the slope will be. So as I see here, there is also an effect of stress. So there is still a significant effect of stress, as you can see, but the effect magnitude is now just 0.4867, right? It's not anymore this 1.3365. So the slope is not so steep. It's like less steep than the one for women. So we could write down beta 1 for men. The estimated beta 1 is now just 0.4867 from this model, where we just include the main effect on the subset of men, but don't discard the data for women for the other half of the data basically. And again, we could also plot this, and we see the data for the men with the best fitting line, which is representing basically the slope right here of 0.4867. So the interesting question, which is the whole point of looking at interactions, is looking at the difference between the slopes for the stress level effect between men and women, and asking, okay, is there a difference? First of all, here apparently there is, and is this difference significant itself? We can talk about the significance of an interaction. Maybe it's just a spurious difference, and it's not really. It just happens to be a little bit different for men and women. But is this difference between the effect magnitudes itself significant, large enough? That's an interesting question we can have hypotheses about as well. And we will see in a moment how we can fit one model overall that includes both the main effect of stress level and the main effect of gender. So we don't do subsetting anymore, but we fit one grand model on the entire data set, and also an effect term which represents precisely the interaction between stress level and gender. In order to do this, we should first, it would be kind of good for us to intuitively interpret the results if we first center all our predictors. That will make the interpretation of the results a bit easier. So as a reminder of how to center a continuous variable, as for example the stress level scores, you would take the sample mean of that variable, and then you would take every individual data point and do that data point, the stress level value, minus the sample mean of stress level. That way you still keep the information of what the differences between stress level are between different data points, but you standardize them in such a way that the sample mean will exactly be 0. That means centering a continuous variable. So we could do that here. We could create a new column, stress underscore C, or whatever we may call it, C centered, and we assign it the result of the computation of saying I want the original stress level value, and I want to subtract from it the average stress level value in my data set. Okay, that is what is happening here. So afterwards we have this new column here, the centered stress level, which can obviously, half of the points will be negative roughly, and half of them will be positive, because on average they should be equal to 0, right? So what is the mean of a centered variable? Obviously 0. That's the question here. So now, once we've done this, and we've also coded the gender variable using scaled sum coding, which in a way is also a sort of centering, right? Because if you do scaled sum coding or any contrast coding where the average of the coded values, assuming like a balanced data set, is 0, then you've also like centered that predictor in a way. So that's what we're doing here. We are assigning scaled sum contrasts, so minus 0.5 being, I guess, the men and 0.5 being the women. Could be the other way around, but I believe that's what it is. So yeah, we've now made it very clear what our predictors are numerically, and as an important property, both of them are now centered. Okay. So now, as I just said before, we want to find out if this difference between the effect magnitudes is really significant or not. That's what we can do now. So what we're doing here next is fitting this model 3, M3, which includes precisely what we want. It will be fit on the entire data set, so no subsetting anymore by gender. And it will have an intercept, of course, and also the main effect of gender, the main effect of stress level in its like centered variant, and the interaction of those two. So what you see there, like this notation, is just a possible way to write that down. So here you can see this written as gender in this Elmer syntax, like gender plus stress C, and then like that whole thing in brackets, and then sort of to the power of 2. Okay, that is a way to write that I want to have this predictor, that predictor, and their interaction. Another way to write the same thing would be to just write gender and then asterisk stress C. That's the same, has the same effect basically. So here with this notation, I'm making it a bit more precise that I just want two-way interactions. Like if I had more predictors, then this 2 would indicate that I just want two-way, like interactions between exactly 2 variables and not more. But I could also have higher order interactions, and this constrains it to 2. But again, I can also write it as gender asterisk stress C. Okay, that means the same thing. And what both of them are basically abbreviations of would be to write explicitly that I want the main effect of gender and then plus the main effect of stress, and then also plus the interaction of gender and stress, with which by itself I would write as gender and then colon and then stress. Okay, so this right here, gender colon stress, is the pure notation in this Elmer syntax for writing the interaction, and this and that would be the main effects. And to abbreviate writing main effect A plus main effect B plus interaction A colon B, I could write either A asterisk B, or I could write, when I'm specifically like talking about two-way interactions, A plus B in brackets, and then this to the power symbol, and then 2, right? All of these are basically doing the same thing. So this is doing the same thing, and this is doing the same thing as well. Just as a short note on the syntax, you see here in the lecture notes that there are some variations, but all of them mean the same thing basically, okay? Right, so we fit a model here with 2 main effects and the interaction between them on the entire data set, and now we get the following results. So here we have the effect magnitude estimates for gender, for stress, and for the interaction of gender and stress. And so as you can see here, the effect of gender, its estimate is 1.5, so roughly, so it means that if I believe women was the one coded positively, so the men had a slightly smaller psychological symptoms score on average, and the one for women is just about 1.5 units higher. But that's just the whole difference between men and women already, just 1.5, and this is a very small difference in a way. So here we also see that it's not significant at all, right? The t-value is just 0.4 and the p-value is hopelessly above 0.05, like at 0.65. So the gender main effect is not really a thing. There is no really significant difference in the average psychological symptoms between men and women. The stress level slope is now 0.91, which is, recall now how we have to read this, like the units are basically psychological symptoms units per stress level unit. So if you go one score of stress on the stress level ladder, like up, you go up 0.9 units on the psychological symptoms scala ladder, okay? So, and here you see, which should not surprise you, exactly that this is now the overall global main effect of stress level, meaning it doesn't differentiate between men and women because we fit it on the entire data. And you see that this is about like roughly the average of what we had seen previously when we differentiated that for men and women in different subsets and running different models. So this 0.9 is kind of like the average, roughly, not exactly, like, but think of it as roughly kind of the average between this 1.33 that we had for women in isolation on this model on the subset for women, and on this of this 0.48 in isolation on the subset just on men. Here, this is like the global effect, so like over the entire data set. It's like 0.9 is the effect magnitude for stress level. And now here, we also have the interaction, which has a magnitude of 0.84 or 8.85. And this is now precisely the difference of effect magnitudes of stress depending on gender, right? So this would be the difference of the stress level effect on women compared to men. And we can see that, again, this roughly matches what we would get by just naively taking the subtraction of this minus this. It would also give us something like 0.85. And notice here that both of these, like both the main effect of stress and the interaction between gender and stress, are significant. So this main effect of stress is very salient. It has a t value of 6.9 and like a very small order of magnitude p-value, like very clear that stress level is associated with psychological symptoms, that it can predict psychological symptoms basically. And we also have quite a salient proof on this data set that here there is a difference in how much, in the extent of how stress affects psychological symptoms depending on the gender of the person. So this effect of a stress level is higher for women than for men, and it is exactly 0.85 units higher. Like that's the difference, okay? That is how you can interpret this output. And you could like be rather confident both about this main effect of stress and about how it is modulated by gender, looking at the results and specifically and at the indicators of significance here in form of the t and the p values. Here you can see another visualization of this very quickly. So again, the scatter plot, stress by symptoms, and now you have the two respective best fitting lines for men and for women. So the difference in their steepness is the interaction basically. So what we see here is the equation for describing a linear model, a linear regression that includes an interaction between two predictors, x1 and x2. And more precisely, here we have the equation for the predicted outcome values. That's why I write predicted here. And that's also the reason why we don't have the epsilon here. And because it's the predictions that we can get after like fitting and estimating the parameter values for the betas in a particular sample, we also don't write just beta, but we write b, which is kind of another way to write beta hat, okay? So the B0 is our estimate for beta 0, B1 is our estimate for beta 1, and so on. So B2 and B3 are the estimates for beta 2 and beta 3. And the equation looks like this. So up until here, it should look very unsurprising. So B0 is the intercept estimate, B1 is the estimate for the slope of, in this case, stress, I believe, and B2 is the estimate of the slope for gender. And B3 is now the estimate for the interaction magnitude, right? And interestingly, for the interaction, we have to do the slope multiplied with the product of the two individual values from the two predictors. So for the interaction, we always have to do like slope times value from predictor 1 times value from predictor 2. That's how we get the interaction term into the equation, right? And So recall that we had used scaled sum coding on our categorical predictor gender. So men were coded as minus 0.5 and women as plus positive 0.5. And so using this formula now, without the error term, because this is about predicted outcomes, basically a formula describing our linear regression result in a way, we can make predictions, like given the values for gender, like a particular value for gender, like 0.5 or minus 0.5 man or woman, and a particular value for stress, we can now use this fitted model described by this equation to predict what it believes to be the most likely value associated with this set of predictor values. Okay, so and we do this by plugging the predictor values into this equation. So we could, for example, take this minus 0.5 for men, and we could plug it into where we have the placeholder xi2, so because that's always the value for the gender. And we would get the simplified formula, which is now specifically for predictions for men. And when we also put a value for stress level in there, then we will get, almost the full result. We also need a value for the estimated betas, of course. But we have that already. We have fitted the model. So once we've done this, we can now generate predictions. So we're going to see how we can do that. So we can extract in R, we can extract these coefficients that we see in the summary of the linear model using the coef function, coef like coefficients. And more specifically, if we want the first one, which represented the intercept in our case, we can do that by running coef of our model object, M3, and then index it with 1, meaning I want the very first coefficient, the beta 0, or like B0, the estimate. And it will give us, this 90.6 as a result, which was our intercept estimate, and put it into this variable now that we have created, the B0. We can do the same for B1, which is the slope for stress level. So we get that from the coef output again, put this into our model. In this case, okay, actually here, because in the model before I had specified it the other way around, I think first gender, then stress, that's why here it's the third one, doesn't matter, right? So B1, for the sake of our example with the mathematical formula, is stress level. B2 is gender. We can also extract it from our model output. And finally, the interaction between stress and gender can also be extracted from this model output, and we save it into B3. So now we basically have all the ingredients that make up our formula, except for the actual values for the two predictors. But these we can put in there now, and we will always get a prediction as a result. So to give you an example, let's say we have a man, that means predictor 2 being minus 0.5, who has a stress level, a measured stress level of 25, meaning value 25 for the first predictor, x1. Now, with this information, we can predict the psychological symptoms score for him, okay? So we can say, we plug all of these into the formula, so we say our predicted y, our predicted psychological symptoms will be equal to the intercept, B0, our estimate for the intercept from the model, plus B1 times 25. That's right, that's the first slope times the value for the first predictor, stress. Then minus 0.5 times B2, minus 0.5 coming from him being a man. And then minus 0.5 times 25 times B3, right? This whole thing together, basically just executing our math formula we saw above, but in R and using the values that we have, we get this prediction of 102, meaning that our best prediction, given this linear model, for a man who has a stress level of 25 is that he will most likely have a psychological symptom score of 102, right? Likewise, we can do the same thing, but for a woman. So we could say we want to compute the predicted number of symptoms for a woman with stress level 25. And here we would have to now, again, run the same formula, the same equation, but instead of putting in minus 0.5, we would have to put in plus 0.5. And as a result, we will get the stress level prediction of 124, right? Or 125 roughly. So we've already talked about multicollinearity, and we've just talked about interactions. And now here is an important issue that we should keep in mind or consider, which is that when we do not center our predictors, then we have a high risk of a lot of multicollinearity in our model. When we do center our predictors, we are basically avoiding, to some extent, multicollinearity between our predictors. But when we don't do it, then, as we can see in form of the variance inflation factor, we will have this problem. So here, what we just did was, in a way, good. Like in the example we just did with stress and gender and their effect on psychological symptoms, because we did, in fact, center our predictors before running the model with the interaction. So if we do the VIF command on the model that we just fit, we can see that the VIF is not much bigger than 1 for each of the predictors, like 1.000, 1.10, and for the interaction 1.103 something. So now that we have an interaction, the interaction also gets a unique VIF value of its own. But all three look good because, you know, they are close to 1, which is the optimal value we could even have. Now, let's say we run the model again, but this time we don't do the centering that we just did. So now we don't center stress to be 0, and we also don't do scale sum coding for gender, but we do just like treatment coding or something. In that case, we will see that if we do that, okay, the original gender and stress uncentered, sum coded, we can see that here we have dramatically higher VIFs for gender and for the interaction, and also to some extent for stress. So it's now at 4, 1.5, and 4.6. Still not above this like threshold of 5 where it should really be a problem, but you can see that it's more problematic. We have more multicollinearity here that is affecting the results of the model. We'll now go on and talk about the next important topic of this lecture, which is outliers and extreme values and how to deal with them. So an outlier, or also called extreme value, is basically a data point which, with regard to some particular variable or combination of variables, is very far off from where all the other data points are. Like, it's clearly not behaving in the same way as the others do. It has like a much larger value for stress, let's say, than all the others. And visually, we could see a few outliers if we stay with our original stress symptoms dataset, like the one that just had stress and psychological symptoms as variables. In that original data file, you can see this plot here of the x and y values. And as you remember, I mean, I had hinted at it already in the first or second video lecture. We can see that there are like this point also, maybe even this point, which are really far off from the overall like cloud of data points. Like, they clearly behave in an odd way. For example, this point here corresponds to a person that has a very unusual stress level score, like much higher than all the others, like at almost 80 stress units. And you can ask yourself, like, is that really meaningful? Was there maybe a mistake in calculating their score, or didn't they fill out the questionnaire properly? These all might be reasons why this data point turns out to extreme, as opposed to really it reflecting, you know, a genuine extreme stress level. But okay, even if it did, the problem is that even if this is like a true, genuinely interesting data point, and this one also, and this one also, the fact that we have this one highly extreme data point, that will heavily skew our best fitting line for the linear regression. Because if we imagine the best fitting line, we can see that if we discard this point, it will look somewhat like this, like I'm doing with my cursor right now. But as soon as I include this very extreme data point, which is not really on that best fitting line that all the other points indicate, this data point alone, because it is so extreme, will have a heavy weight in determining the best fitting line. So it will change the best fitting line to something like this, just this one data point. And there it really matters suddenly for the analysis if we have these extreme data points or not, and how to deal with them. There are various ways you could deal with this that we are going to look at in a moment. But here maybe another example in the stress symptoms 3.txt, that was like the other one of the other variants of this kind of data which we looked at, which is saved in our 3.txt file here, including the gender. Here we have four, this one maybe, it's probably not an outlier, but maybe this, and this. Just visually, you could classify them as outliers, okay? Another example here is a data set which contains EEG data. That is, from electroencephalography, where people have these electrodes on their heads, and then you measure their brain activity while they're doing certain tasks, for example, reading in psycholinguistics. Here we have a different kind of plot. Here we have a density plot of the resulting variable, but the idea is the same. So the resulting variable is this latency on the EEG signal, probably something like in microvolts, or maybe it's actually the response time. Actually, it's maybe the response time, but there was also an EEG experiment parallel to it, so might be response times after all. Anyway, what you can see here in this dependent variable is that you have this like density plot of the. You could also do a histogram. Here we have a density plot of the sample of data itself, and you see, okay, it looks rather normal here, but there are some bumps like at very extreme parts of the scale. For example, here there seems to be a bump, so there might be an actual data point at like 2000 or higher, if that's like in milliseconds, the latency, and that's kind of odd. Like that data point, does it really reflect the same kind of processes as like all of these data points that are much closer to this distribution like segment of the scale here? Like that's something that could worry us. And there's also another one, also this EEG data set, but complemented with reading times apparently, where you again have this variable latency, and here you see that this density plot now just by default, without specifying anything, has this huge x-axis, and the reason is that probably somewhere around here between 5,000 and 6,000 milliseconds, I guess, there's like one or two very extreme data points, which obviously have nothing to do with the data generative process that generated the vast majority of data points. Okay, so another way to basically look at your data, visualize your data, and see if there are potential outliers. And if this scaling of the plot function gives you a default automatic scale of something up to 6,000, then you can be sure that there is something going on here, like one or two extreme values, like outliers, which lie so far beyond where everything else, where all the other action is happening. So I already hinted at what could be the problem. Basically, the main problem issue with outliers is that they can greatly influence the outcome and sort of distort the outcome of a statistical analysis. Also, it is the case that most of our statistical tests assume certain things about our data, for example, that they are normally distributed, and they only really work or like make sense, like the outputs from our statistical tests, if those assumptions are met. But if I have huge outliers, this kind of thing could be normal, but not if there's like huge outliers far beyond where the main mode of this distribution is. So once I have outliers in my data, I'm not really meeting the assumptions of my statistical tests anymore, because they assume that the data should look roughly normally distributed, let's say in a linear model, for example. So that's a problem. And two other related problems are, of course, okay, we looked at this visually by now, so we saw, for example, these plots here, and just by eyeballing it, I told you this guy should be an outlier, this one and this one should be considered an outlier, maybe this one too. But we don't really have just doing this doesn't really give us a quantitative precise criterion. Like, is it just, eyeballing and seeing what looks far off, or is there some more objective way to classify a point as an outlier? So that's a whole problem of its own, like how to identify an outlier, how to basically define that the point is an outlier. And then also the question arises, when you run your statistical analysis, should you remove the outliers then, or should you keep them in the model? And so there's no totally 100% correct solution or like answer to these questions, but we're going to now go through various proposals, various ways to deal with this outlier problem in general. So one thing you could do is to always keep all data points in, like not taking care of like removing outliers at all. In fact, if you run a linear mixed effects model, then outliers are also less dramatic, because the hierarchical structure of the mixed model can to some extent accommodate for the extremeness of the outlier without distorting the overall regression result. If you want to read more on why that is the case, you can maybe Google or look up the key term shrinkage here. Another thing you can do is to remove outliers before you run the analysis. So you might define some criteria, let's say. A priori, you might say, okay, I have my dependent variable, could be stress level, could be reading times or whatever. And I'm going to say, before I run any analysis, I want to remove any data points that are further than, let's say, 2 standard deviations or 3 standard deviations or whatever criterion you set away from the sample mean. That's something you could do, and then run your analysis based on this criterion and just include points that are within a reasonable range away from the sample mean, but not more than, let's say, 3 standard deviations. That's sort of an objective way, I guess, to classify the outlier. You don't have to look at it visually. You could still do what we did just now. It's sort of a more subjective thing now, to look at the plot, just visualize your data and then visually identify which data points are outliers. That's not wrong, but of course there is some risk of it being subjective and you having too many degrees of freedom in what you can do and not do when you run the analysis. So that might get you some criticism if you don't have a very clear objective criterion about how you excluded outliers. Another possible way of defining a robust, clear-cut criterion would be to use hard cut-off thresholds as opposed to saying something in terms of standard deviations. So instead of saying I want to remove any points that are 3 standard deviations below or above my sample mean, I could also say, with regard to reading times, let's say, that I want to exclude any reading time in a self-paced reading task maybe that is below 400 milliseconds. And I also want to exclude any reading time that is above 2000 milliseconds. There's also a concept called robust regression, which is sort of a variant of regression that sort of is more suited to tackling outliers. It's not something we're going to cover in this course, but you can look it up if you want. Also, there are ways to actually quantify how much your results are influenced by single data points. And the metrics we're going to look at are either Cook's distance, or also there's actually this influence.me package, which includes Cook's distance as well, but also suitable for mixed models, and also some other metrics like df betas, which we're going to look at in a moment. So first, Cook's distance by itself works as follows. So Cook's distance is this metric, this numerical metric, which tells you basically, given your data and given the linear model you want to fit, or that you've already fitted in R in this case, can you identify data points that have a large influence on the results? And so what it does, so it will give us a certain number for each data point, which tells us how big the influence of this data point is on the results. If this influence of this one data point is very big, it means that it's probably an outlier which has a substantial effect on the results. So not every outlier will have a big Cook's distance, because if you look at the plot from before, you could imagine that you have your best fitting line that's going straight through like this. And then if you had an outlier here, that wouldn't have a big Cook's distance, because it's, even though it's an extreme value, it's perfectly aligned with the linear trend of the rest of the data points. Whereas if you have an outlier here, let's say, or here, then this will have a large Cook's distance, because just including this one point will, already change the best fitting line to some non-trivial extent. So that's how you can think of the influence that a point has on the regression results. So going back to our section on Cook's distance here, what this does under the hood basically is it computes the regression model many times, and each time without a particular data point. So it will compute the same linear regression model, but excluding data point 1, okay? And then it will run the linear regression model again, but this time excluding data point 2. And each time it does this, it will compare the regression results against the model that includes all data points, to basically see for each of the data points how much does it make a difference including it or not including it. Okay. And so in R, we can use the Cook's distance using an inbuilt function from the linear modeling functions. So we first can fit, a linear model, let's say, of our original data set with psychological symptoms and stress. And then we want to, just do the simple linear regression. So we fit that, we put that into a model called M5 here, and here's the model output. Okay, so this gives us our result that we've already seen a couple of times, that the stress level has a significant influence on the psychological symptom score of about 0.78. And now we can run the Cook's dot distance function on the output, like on the model object that the LM function created for us. And once we do this, we get basically a vector which includes the Cook's distances for all the individual data points in this data set. And higher Cook's distance values mean that the influence of this data point is larger onto the result of the regression, whereas like smaller Cook's distance values means that they don't influence the outcome so much. So what we could do now, for example, is to filter out the data points that, based on Cook's distance, are the most influential ones on the result of the regression. Okay, so what we could do, for example, is to set this threshold of saying we want to compute the average Cook's distance across this entire set of Cook's distances for all of our individual data points. We can compute an average of that, right? And we can say, I want to know which data points are bigger, the data points whose Cook's distance is bigger than 3 times the average Cook's distance. Okay, so we take the mean Cook's distance, we say that times 3. Cook's distance can only ever be positive, and now we want to see which data points have a Cook's distance higher than that, higher than the average, higher than 3 times the average, I mean. And in this case, so here we could save them into a vector just to have a look at them quickly and print out this vector, INFL, influence. And we see that there are exactly 4 data points in this overall data set for the stress symptoms data, which meet this requirement, which pass this threshold. And you can see that it's here, in this case, the 19th data point, the 55th data point, the 88th data point, and the 90th data point. And so here you can see their respective Cook's distance values. Another functionality in R that is kind of related is the influence.me package. You can do various things with it. It's kind of like the Swiss Army knife for all these kind of metrics that tell you something about the influence of individual data points or even groups of data points. We'll get to that. On the regression result, to basically find influential outliers or groups of outliers even. And so the influence.me package is especially suited, or it can also accommodate mixed models. If you fit a linear mixed model, for example, using LME4, using the Elmer function, then you can use the influence.me package to get things like Cook's distances or other metrics out of it, as we'll see now. So it's a package you have to install, of course. At least I believe you have to install it. It doesn't come shipped with R by default, but you can use install.packages, just as you would install any package that's on CRAN. And here we have this data set with the EEG and reading time data. And here I believe we are concerned about the latency, which is, I think, just the reading time. Okay, so this is about different, this variable is the age of acquisition, so I think it's maybe something like bilingualism data, and you have different participants who all speak this target language as their second language, and one interesting variable that differs between them is at what age they started learning that language, or at what age they acquired the language. So comparing a person who learned English as a second language starting from first grade versus starting from, I don't know, adulthood or something in the more extreme case. And here we fit a linear mixed model because we have multiple observations per participant. So PPID is the group that describes the participants. Okay, and so here you want to have here in this case we fit it with the subject, like by participant intercept only. So we want to have adjustments for the intercept for each participant individually. Okay, classical simple mixed model situation. And once we fitted this model using the Elmer function, we can use the influence function from this influence.me package to like create this object which we can save in this variable called stex.obs here, which will include like summarize many different aspects like Cook's distance, but also other metrics for each individual data point. In this case, running it like this first. So what you can see here, I'm going to skip back to what I just scrolled over, but like first things first. So in this stex.obs object that we just created further above, we could now run the cooks.distance function on that, and now we would get Cook's distance values for individual data points, as in the way that we did it before. Okay, so that's one thing we can do, and that's like data point specific now, just as before for the simple linear regression model. But you know, the interesting question with hierarchical models is, of course, what about, you know, not only individual data points that behave oddly, but maybe you also want to see if there is like an outlier item, or okay, we don't have items here, but like an outlier participant. So maybe is there, like in this data set, is there maybe one particular person that, you know, that kind of behaved very differently from all the others, or maybe didn't take the test seriously, or like was on drugs or something weird like that. So they kind of really have very different results from all the others, and clearly their data doesn't come from the same data generative process as the data from all the other people does. So what we could do here is run this influence function again on the model object from the Elmer function. But this time we're going to give it like this other argument, which is group equals to, and then whatever our group level category is. For example, PPID is the category that specifies the individual participants. So we're going to give it that and save it as, you know, we might call it stex.obs.participant, you know, making sure that this output is now with regard to this participant level distinction. And now we can run the Cook's distance again, or like compute it. But as opposed to before, we now want to have the Cook's distance for a particular participant, as opposed to just a single data point. So the way to achieve this would be to now run the cooks.distance function again, but this time, well, on this output stex.obs.participant that we created using this additional argument group by PPID, okay? And now the result will show us this. So we will have a Cook's distance value for each individual subject or participant. So S101 is like the first participant, I guess. S102 is the second one. And so we can see basically how much every single person influences the results. There is another metric that is part of the influence.me package, which are the so-called DF betas, which is basically the standardized difference in the estimated parameters. What that means, a bit more intuitively, is maybe understandable when we see this output here. So if we do df betas and run this function on the object that we created when we did this influence.me functionality applied to the by participant data, now we also get different values for each participant, and we also get like a distinction between intercept and slope. And so what these numbers basically mean is they describe the difference of, you know, what the intercept would be when we include this participant versus fitting the same model but excluding that participant. Like here you can see how much this would change the intercept estimate just by removing or excluding this one person. Or the same thing, you know, for the slope, we could see here sort of how much, like by how much the estimated slope for age of acquisition would change just by including or removing this particular person from the data set. Okay, that's the part about outliers. So the TLDR is, of course, you know, have some criteria and have some strategy to deal with outliers, keep them, remove them, define thresholds for removing them. There's no really very magical one-size-fits-all solution, but the important thing is to be consistent with what you wanted to plan, what you had planned to do before seeing the data. Like, don't try thousands of different analyses with different variants just to get, to squeeze out a result you want to have. That would be bad. But be consistent and justify the strategy you use, basically. Okay, so the next and last chapter of this lecture is about checking model assumptions. So when you run a linear model, there are certain assumptions that basically you implicitly make when you take the linear model framework and apply it to some data, and your results are only really valid or only really make sense if your assumptions are met, or like roughly met. Okay, if your data are not really satisfying the assumptions of the linear regression, you will still get an output, but maybe it doesn't really mean anything, or like there's some caveats to interpreting it. So one thing that you should kind of do when you run an analysis involving a linear regression or linear mixed model is to check if your model assumptions are met. There are three main assumptions that we want to look at here. The first one being that the residual errors are normally distributed around zero, meaning that if you think of the linear regression, maybe this pencil. If you think of the linear regression and just a simple example and the best fitting line, so the residuals are always these distances that the observed data are away from the predicted data. And if you were to take this value, maybe like minus 0.2, this value maybe 0.1, this one maybe minus 0.25, and put them all into one bucket, and then were to visualize those, like their distribution, you're assuming in a linear model that the residuals are normally distributed. That like the residuals, the error terms, come from some normal distribution with mean zero. That's part of the assumption. And some standard deviation sigma that we don't know, that the model also implicitly estimates. And if you were to see that your residuals are not following a normal distribution, but some other kind of weird skewed distribution, that would violate this assumption about normality of the residual errors. Another thing is that the errors are independent. That's the second assumption, independence of errors. This means basically that all of these data points of residuals, if I put them into one bucket, there is no way of telling, of being able to predict one residual error based on the others. Like they are all identically and independently distributed. So there is no correlations between subgroups of the residuals. That's very important, that the errors are independent of each other. That's another assumption. And the third assumption is the assumption of homoscedasticity, also known as homogeneity of variance. This basically means that the errors do not depend on the independent variable. They do not differ between different levels of the factor. Let me draw another plot just to give you the idea a bit more clearly. So if this was my predictor, x, this is my y, and now let's say I would find something like this. So here's maybe my best fitting line, and now here I have my observed data. So here what you would see is that you can find the best fitting line, and it will be based on minimizing the sum of squared residuals, but there's something weird going on here in this particular example, namely that the residuals are on average much slower with a smaller value of the predictor, but they tend to be much larger with a larger value of the predictor. That is not okay. That is violating the assumption of homoscedasticity. So these are three assumptions, very essential assumptions for linear modeling. And there are different ways to check if these assumptions are met in a given data set. So that's what we are going to look at now. The first assumption, as I said, was about the normality of errors. So that the errors, the residuals come from a normal distribution, that they look roughly like that. Okay. So one thing we could do is take the residuals from our model. We can do this for a simple or even for a mixed linear model, I believe, using the resid function, resid like residual, apply it on the model, and then we can do a density plot of this and basically visualize them as a, as if they were like a probability distribution. So this is what you get here, and notice that here we kind of have this similar issue that we also had when we just plotted the raw latencies, namely that, there is a reason why this x-axis by default is like so wide, and why it includes these like very high parts of the like intervals like around 4,000, 5,000. The reason is that there's some extreme data point that we also saw in the raw visualization basically, which is around like 4,000, 5,000 big, and that also obviously corresponds to like a rather big residual that you can find in the plot of residuals here. So that's kind of sketchy. It's not really, I mean, without this, okay, like this part looks normal, but it's really a problem that we have a residual error that's so far off from the rest. That could be kind of maybe something to worry about. So this is one way to check it, like just, visualize the residuals as a density plot, or alternatively you could also try a histogram. Okay, you should like check that they look roughly like symmetrically like a bell curve. Then it means kind of intuitively that they are normally distributed. Another way is to do a so-called QQ plot using the QQ plot function. The QQ plot is a plot that checks how well the residuals align with the theoretical, like the assumed distribution, the normal distribution. And so the way this will look is that it's like a two-dimensional plot, and on one axis we have the observed residuals. On the other we have the ideal residuals, like the values the residuals should have had if they were indeed perfectly normally distributed. And so if the residuals are normal, then they should, in the QQ plot, as we see here, they should lie on this like line drawn here. But if they are not normal, then they deviate from this diagonal line. And here we can see there is some deviation, like a little bit here, and then some dramatic, very concerning deviation of like two extreme values over here. So I zoom a bit in, so you can see this like blue line. That would be the ideal case. If my residuals were perfectly normal, then all of these small circles should be on that blue line. Obviously, like they will never be exactly on the blue line, but reasonably on the blue line. You can see here already that there is some deviation from perfect normality going on around here. So even like among data points that are not outliers. So it's not perfectly normal, but okay, reasonably enough. But the real issue are these two guys, right? So these two are clearly very far off any reasonable position that would sort of make us have a justified assumption of them being normally distributed. Like they are somewhere else, okay? They are not clearly not on this blue diagonal, which would indicate perfect normality. So that these are data points 37 and 18. Yeah, we can also run some command to like print out which data points the outliers are here. Okay, let me zoom back out again. Right, so that's the QQ plot. You see a blue diagonal where the values should lie if it was normal, but if they are not exactly on the blue diagonal, or depending on how far off they are, it tells us how extreme the assumption of normality is violated, basically. Now, the next thing is we can maybe try to remove these, I guess, two, in this case, outlier residuals that we saw above, and then see how, the QQ plot visualization will change. So we can do this. I mean, it happens that, these two data points had latencies of above 2000. So if we set a strict cutoff of latency having to be less than 2000 milliseconds, then we can, create this subset and, plot the dependent variable again. So that's now the new plot that has, by default, now a much smaller range on the x-axis, because, these data points, these very few rare but influential data points above 2000 milliseconds have been removed. So that's the new plot. It's still, it looks a bit better. It's still a bit skewed, right? So you can expect that it's not perfectly normal, but it looks better, of course, than having these very extreme guys in there as well. And now let's do a QQ plot of this data without the extreme outliers. We have to like fit the model and then extract the residuals and perform the QQ plot function on the residuals. Here it is using the residuals function, not resid. Okay, small difference when you have to use QQplot. And here you can see this. So here we have the blue line, where the the residuals should lie ideally if we had a perfectly normal distribution of residuals. And the black small circles is the actual observed residuals. So up until quantiles of like 1 roughly, it looks fine, but then here the residuals start to deviate to some extent, from what they would have to be assuming perfect normality. And this kind of corresponds to this skew that we can also see here visually, right? So here, this skew to the right, we can see that this has a long tail, whereas on the left side, it's, the tail is much less wide. So that's asymmetry. You can also basically appreciate it in another way by looking at this QQ-plot, where now these values for the higher quantiles deviate from what would be assumed under a perfectly normal distribution of residuals. So TLDR, that's better, but still not perfect, but maybe reasonable enough to like run the model and be fine with it, even though strictly speaking we are not exactly matching the assumption of normality here. Okay, so the question could be, of course, what to do when we see that our variable is not really normally distributed. There are different strategies to deal with it. If the violation is not so big, maybe you can ignore it, but I guess for reading times, it's actually kind of the default pattern to see like a strong tail to the right. So you might wonder, maybe we can do something about the reading times to make them more normal, to apply a so-called transformation. And for response times, it's actually common and even good practice to not fit a model on raw response or reading times, but to actually apply some transformation that takes the values in milliseconds and transforms them mathematically into something that's more normally distributed. One such transformation, which is very popular in linguistics and psychology, is the logarithmic transformation, which would just mean you take the logarithm of the raw reading time and you get a so-called log reading time out of it, and that will be your new dependent variable. Another is the so-called inverse transformation, which is basically taking -1 divided by the raw reading time, or the raw whatever the dependent variable is value. Both of these kind of do a similar thing of like kind of reducing this right skew or like large right tail that some variables have, for example, reaction times and reading times. And we can maybe visualize this for a moment. So here, let's do the density plot again of our data we had before, the latency data from this EEG and reading times data set, but without any values above 2000 milliseconds. So this will give us this plot here. So you can see, it has this long tail to the right. That's the untransformed data. Now we can do the logarithm of the latency, the log transformation basically. And now we can see this. So that's already more symmetric, than this. Has a much larger skew. This skew, well, there's still some skew to the right here. It's not perfect, but it's already much more close to resembling a symmetric bell curve, right? And the other transformation is, the inverse transformation, so -1 divided by the reading time. If we do that, we get this result here that even looks even better to some extent, right? So here we have almost a symmetric curve now. So that's a very useful transformation to make the values that we are working with for the linear modeling more normally distributed. So we can do the corresponding QQ plots as well. So here, let's say we do the QQ plot of fitting the inverse transformation as the dependent variable now, as opposed to the raw latency, the raw reading time. And what you will get is this QQ plot. So as you can see, that is much nicer than what we had originally. Like, recall the original QQ plot on the raw data. There was like this strong drift away from the ideal, blue line, where it would indicate perfect normality. When we take the inverse transformed data, on the other hand, we have like a much more, we are much closer to the ideal. We're much closer to to assuming that our residuals are really normally distributed, as you can see here. Or the other transformation, the log transformation, we can do the same thing. So visualize the QQ plot for the log transformation, and that's a bit worse actually in this case than the inverse one, but it's still better than the raw reading times. So here you can see clearly, I mean, there's still, you know, these outliers, which, oh, maybe it's like the original outliers that were in the original data set. So the ones that we removed, basically, you actually have to compare, yeah, 37 and 18. So these were these very extreme crazy guys. So this was the original QQ plot, basically. And so now with the inverse transformation, which appears to perform best in this case, they are still, you know, off the ideal line, but not so extreme anymore. So we basically have transformed them to a dimension, to a value, to a scale, basically the inverse scale, where they are much less dramatic than on the raw scale, as you can see here. And here for the log transform, well, they still pose some kind of problem, not as big as in the raw data, of course, but you know, they are still uncomfortably far off this blue line, which would indicate perfect normal distribution. So maybe even with the log transform, I might want to remove those two outliers. For the inverse transform, I can even keep them in the data. I don't have to necessarily remove them because, you know, they're not as dramatic anymore. So that's what these transformations can do to help you re-establish normality of residuals. There's another way to test for normality a bit more formally, which is the so-called Box-Cox test. And here in R, this will also give us an information about which transformation we should apply to make the data more normal. Okay, so there's this Box-Cox function in R, which we can apply to a fitted linear model. For example, like let's say this linear model predicting latency based on age of acquisition. And so the output of this Box-Cox function in R is actually this plot right here that you can see, where you have to read it as follows. So here, where this lambda axis, which looks maybe a bit mysterious for a moment, but where the lambda is 1, and the value that I get here, this log likelihood value, this basically represents a log likelihood that indicates how likely it is that my residuals are normal. Okay, so and you can see that this is like has a certain likelihood value. Okay, and this lambda represents different kinds of transformations we could make. It's actually kind of a continuum of possible transformations, but the two possible transformations that we're really interested in is either the log transformation, which is what 0 represents, lambda equals 0, or the inverse transformation, which is what lambda equal -1 represents. Okay, and we can read off this plot here how like this log likelihood changes depending on if I'm in the situation of no transformation, which is lambda 1, of log transformation, which is lambda 0, or inverse transformation, which is lambda -1. And so here, if you just have to pick among those three possible discrete variants, this output would indicate to you that with our given data set, the most sensible transformation that basically maximizes how normal the data look will be the inverse transformation. Because you can see that this graph has a maximum, which is, I mean, it's not at -1, it's actually a bit to the left of -1, at -1.3, let's say. So there is a possible kind of not so intuitive transformation that would correspond to lambda equal -1.2, I guess, which would be the optimal transformation we could do. But we want to limit ourselves really to these three options in order to keep the transformed variables somewhat interpretable. So we can take the inverse transformation, which corresponds to this lambda equal -1, where we will already get quite a high log likelihood out of this. Not, you know, the ideal one that's even a bit to the left of this, but good enough for us to think of the data as approximately normal, right? So that is, you know, how you can decide somewhat systematically on which transformation to use on data that have a skew to the right, for example, reading times, reaction times, using the Box-Cox test. Again, the important thing is though that you should, just as for what we discussed earlier, you should always kind of be consistent with regard to the decisions you apply. So ideally already define from the start which transformation you will use, or define something like I'm going to use the box-Cox test to determine the correct transformation. But like don't try millions of different things just to get the desired result. I'm repeating myself, but it's really important for you to be honest with which analysis you had in mind when you collected the data and sticking with it, or if you still change it, to at least transparently report that. All right, so that brings us to the next model assumption, which I mentioned, which is about the independence of residual errors. We can also check this assumption. And one possible way to check this is by computing the autocorrelation between two adjacent residuals. So we can always take pairs of like, let's say the residual I, like the ith residual, and then take the residual I plus 1. So like for two adjacent data points in the list of data. And then compute the autocorrelation for all of the residuals and see if there are like if there's any pair of data points of adjacent data points where the autocorrelation is very high. Okay, that's something you ideally don't want to see because that would violate the independence assumption. So in the result here, which we can obtain by applying this ACF to the residuals function applied to the model that we fitted already, which in this case was a linear mixed model, we see this as a result, and we can see that overall, it looks quite good. I mean, there's this one case where there is like a strong autocorrelation indicated here, but that seems to be like a one-off. Like overall, the residuals appear to be not autocorrelated, which means that they are independent. Notice that like a small thing to keep in mind here is that here we had fitted mixed effects model on these data, because they were hierarchical data. We have subgroups of data points pertaining to particular subjects and subgroups of data points, or in some cases even subgroups of data points pertaining to particular items. In this case, we just had the participant level grouping, okay? Thanks to the fact that we have fitted a linear mixed model here in M7, we get a nice result which tells us that there are almost no autocorrelations happening, or like they are very low, like close to zero. Spare for this like one-off, okay? If we had fitted a simple linear model on the like unaggregated repeated measures data, then we would see that the autocorrelation is much more dramatic, because now there would be a correlation between residuals pertaining to Tom, to like one particular participant, because they will share certain properties, like maybe Tom has higher variance than another person. Then we would have a problem, right? Because then there would be autocorrelation, and this we can see here. So if we run ACF on a model where what we shouldn't do, which is a bad thing to do, to fit a model on repeated measures data without aggregating and without accounting for random effects, then we would see this much higher autocorrelation. So here with the linear mixed model, we have a very nice situation because we are taking into account this hierarchical structure of our data, so our autocorrelation is like barely even crossing 0.2. But if we fit a simple linear model, then we have this plot here where we have autocorrelations of almost 0.4, which is bad. Okay, so here you can see the benefit of fitting a linear mixed model, because that takes into account our hierarchical data structure. The next assumption is homoscedasticity. As I mentioned in the introduction of this chapter, we basically want to ascertain that the variance, like the size of how far the residuals are away from zero, that is not dependent on the particular level of the predictor that I'm at. Like that, there is no situation like this. We don't want to have this, and we want to check this. We want to have something like that. And in order to check for homoscedasticity visually, we can plot residuals against fitted values. And in fact, there is actually an inbuilt R diagnostics plot that does precisely this. We can get it by running these 2 lines of R code with respect to our fitted linear model M7 or linear mixed model. Either way would work. And the output looks like this. So what you see here on the x-axis is basically predicted outcome values, so predicted latencies in this case that can range from 600 milliseconds from 1000 milliseconds. They can range because there is a linear relationship that has been predicted in the fitted model where as we, let's say for example, have one predictor, as we increase in the age of acquisition, maybe the reading time decreases or increases or whatever. So this fitted linear model can predict a range of different fitted values. And here we basically see, the data points that, where they would land. Each circle is an individual data point, and, where its fitted value would be based on the predictor variables. And what you can see on the vertical axis here is the residual error corresponding to a particular data point plotted here. So if we take, for example, this data point right here, so this one had, like where my cursor is right here, this blue circle, this data point has a residual of plus 500 and something, 550 maybe, and it has a predicted value for the outcome variable of 670 or 80, let's say. So that's what this plot, shows us, like fitted predicted values for the outcome variable on one axis, and on the other axis the residual errors. And now the way to look at this plot and understand this plot with regard to homoscedasticity is the following. So if we would see that the spread of residuals is like larger or thinner depending on the magnitude of the predicted y values, which is related to our predictors, of course, then we would have a problem, because let's say, for example, we would see this plot like this, that there's maybe little bit of variation for like smaller predicted y values, but then more spread in the residuals as we get to larger predicted y values. Like this would be an extreme case of homoscedasticity being violated. Like this is clearly not homoscedastic. Ideally, for homoscedasticity, we want to see that no matter where we are on the axis of the predicted values, we want to have roughly the same spread for the residuals. So this is homoscedastic. This clearly isn't. The general take-home message of this lecture, which I know covered a lot, is basically what you can see here. So when you use linear modeling and you're applying it to a specific data set, you should make sure that the assumptions are met, as we just said. You should also take decisions. There are many possible decisions to take, like whether to remove outliers or not remove them, how to decide what an outlier is, what threshold you set for that, basically, if you do, and if you potentially maybe apply some transformation on your dependent variable. Like all of these are decisions that you can take. Like there is no definite right or wrong, even though there are certain indications based on the diagnostics that we can do, that we saw in this lecture. The important thing, as I've repeated over and over again, but I'm going to tell you again one last time, is to take these decisions before looking at your results, right? Ideally, even before you collect your data, because your decisions on what transformation to apply, what kind of outliers to remove, if you want to remove them, all of this should never depend on like the output of an analysis. Like the worst case that you could do, would be to like run an analysis, see disappointingly that your result is not significant, then, try something else, like try a transformation or try to remove some outliers depending on different criteria, and then run again. And then after trial and error 10 times, maybe you end up with one analysis where your p-value is barely below 0.05 and you're happy. You shouldn't be happy. Like maybe you can be happy because you can sell your results, but science wouldn't be happy because, likely this would like flood the body of published research with results that aren't really significant. They are only significant if we try like every possible thing we could do until we get a p-value of below 0.05. So really being committed to analysis plan which we define a priori before looking at the results, is an essential component of good research practices. And it's okay if we like looking after the results, if we want to run a different analysis. It's not by default bad, but we should be honest about it. We should report that we had this one analysis that we wanted to run a priori. We saw that the results look this certain way, maybe they're not significant, and then as an exploratory but transparently described additional analysis, we ran, let's say, an analysis with a transformation on the GV or with outliers being removed. Like, that is fine. If you're honest about your chronological order of running analyses and the motivations behind running them, and the specific decisions that were taken, that is okay. But don't hide that and just report the one analysis among the 10 you tried which gave you the desired result. One way to really make sure and also be honest with oneself and the research community that one has, one is committed to a analysis plan that was devised before looking at the data or even before collecting the data, is the so-called tool of pre-registration. Pre-registration is basically writing up an analysis plan describing in some detail what kind of models you will run, what kind of decisions you will take, what criteria you will do, you will apply to like remove outliers or decide on a transformation or whatnot, and to compile this into like a short but like very clear and unambiguous document. And then there are platforms like OSF or aspredicted.org where you can upload such documents with a timestamp. So you will have sort of a proof with a timestamp that documents what analysis you wanted to run. Then you can collect your data and analyze it based on your pre-registration. And then your claims, if you find something, are also much more credible because you can show the reader of your paper or of your, wherever you publish your study, that you in fact ran exactly the analyses you wanted to run anyway before seeing the data. All right, so these are just some final thoughts you should take home from this like general walk through different kinds of issues related to linear modeling. And that's all for today. So see you guys next week then in the next video lecture.